Hi everyone, I'm Andrew, and I'm presenting our EMNLP paper, Reasoning Paths with Reference Objects, Elicit Quantitative Spatial Reasoning in Large Vision Language Models. This is a joint work with Rafi, Sanyat, and David. Before diving into any details, let me put out our key contributions. First, we introduce a new benchmark for large vision language models, targeting on quantitative spatial reasoning. We formulate quantitative spatial reasoning as a visual question answering problem. Given an image and a question querying a physical distance in the image, the model needs to answer the value of the query distance. This task has previously been shown to be challenging for strong VOM, such as GPT-4v. We call this benchmark Q-Spatial Bench. The benchmark is featuring high precision answers and a set of freshly captured images. With the high-quality benchmark, we first evaluate popular closed-source VOMs. As suggested in the prior works, most VOM perform poorly in our benchmark. However, perhaps surprisingly, GPT-4o outperformed others by a large margin. We take a deep dive into the responses from GPT-4o and develop a new prompting technique called Spatial Prompt that consistently improves the performances across all evaluated VOMs. Okay, so let's dive into the details of our work. First of all, why do we even care about spatial reasoning? Nowadays, almost every smart device has access to large language models. They are helping us in coding, language translation, document reading, etc. However, though they are excel in the digital world, LLMs or VLMs struggles in the physical world. When placing them in the real-world settings, they are lost in space and struggle to recognize even the simple left and right concept. To further expand the impacts of AI, it is important to equip our agents with such spatial intelligence. Spatial reasoning isn't a new concept. Early datasets like MS COCO already incorporate it. Recently, more and more datasets have been specifically designed to evaluate spatial reasoning skills. However, most spatial reasoning datasets are handling spatial relationships. The question here is, are they enough for the real world? For an agent to understand the real world, it is important to perform spatial reasoning in a quantitative manner. For example, the agent should know if the space in the corner is enough to fit a 3-seater sofa, or if we can fit a 50-inch office table between the bed and the wall. Measuring this distance with millimeter precision from a single image might not be feasible. However, humans are great at estimating the rough distances, especially in the real world. To facilitate the research of quantitative spatial reasoning, we curate a high-precision VQA dataset. In Q-Spatial Bench, we have two splits, Q-Spatial ScanNet and Q-Spatial++. Here, we show some example images in our benchmark and some basic stats of them. Note that to construct Q-Spatial++, we capture our own images to ensure that none of them are included in the training of any VOMs. Our benchmark features high-precision answers. For Q-Spatial ScanNet, we specify the endpoints of the query distance and annotate them in the point clouds. For Q-Spatial++, since we capture the image ourselves, we simply measure them using physical tools such as measuring tapes. Our benchmark is the first publicly available benchmark targeting on quantitative spatial reasoning. The benchmark is now hosted at Hugging Face, and feel free to pause the video and go check it out. So how do popular VOMs perform in Q-Spatial Bench? As we shown earlier, GPT-4o outperforms others with a large margin. In Q-Spatial Bench, GPT-4o achieved more than 60 points in success rate in both splits, where other VOMs such as GPT-4v achieved no more than 30 points in success rate. This is perhaps surprising. Before GPT-4o, prior work suggests that the state-of-the-art VOMs struggled at quantitative spatial reasoning. Here are the streamlined table from the prior work evaluated in the same metric. The strong models like GPT-4v achieved poor performance as well. So when we were observing this drastic improvement, we are interested in the gap in between. What can be the secret sauce in GPT-4o? Of course, we do not know the training recipe or the data used in GPT-4o, so we need to find another way. We started by looking at the responses from GPT-4o, and interestingly, we find that GPT-4o tends to use reference object in its reasoning paths and estimate the answer at the end. Here's an example. We asked it to estimate the height of the stack of towels. Specifically, it uses the height of the counter as references to perform spatial reasoning. Note that the height of the counter is usually around the waist of the human body, so it's easier to estimate. We therefore have the following hypothesis. Using reference object for quantitative spatial reasoning leads to strong performances. To validate our hypothesis, we collect the GPT-4o responses from both splits and use a logistic regression model for the analysis. For each response, we can derive the following 4 variables. First, if the response is considered as a success or not. Second, the source of the data split. Third, the ground truth distance. Lastly, if the response uses any reference object. By using the success of each response as target, we fit a logistic regression model on them. We find that the first 2 variables affect the success variable very little. In contrast, using reference object in the response increased the odds of the success variable by more than 250% in a statistically significant manner. Inspired by this, we propose Spatial prompt that encourages VLM to reason with reference objects. We have 2 versions of Spatial prompt, depends on model's instruction following capabilities. In our experiment, we find that all VLMs, including GPT-4o, consistently improve their performances in quantitative spatial reasoning. This suggests that, to some extent, quantitative spatial reasoning is already equipped in these models, and we just need a better prompt to elicit them for a better estimation. Regardless of the success in closed-source VLMs, we find that open-source VLMs demonstrate inconsistent improvement when given spatial prompt. Our guess is that smaller models are not equipped with strong enough reasoning capabilities. Similar to the findings identified in the Chain of Thought paper, where they identified that models smaller than 100 billions model parameters struggles to perform chain of thought reasoning. To understand more details of our benchmark, you can now load them via Hugging Face API with a single line of code. Thanks for your attention.